stacks. In this video, we're going to be going through a reminder of what a data structure is. Again, another reminder of what an array is, because we're going to be using an array in this video. What an abstract data type is in data structure. In particular, we're going to be looking at what a stack is and the basics behind stacks. Finding out why we bother learning about stacks, a little past paper question, and then we're going to go on and build our own stack in C#. C# has built-in stacks, but we're going to go and build our own. So to begin with then, what is a data structure? Data structures, they're containers in which we store information. There's lots of different types that exist, and depending on your application and depending on the data you wish to store, it makes a difference as to which type of data structures we are interested in choosing. And yeah, it's the programmer that has to decide which one's the best one to use, depending on a given scenario and situation. A data structure you're already familiar with is an array. So an array is data structure that you've already used. It's got an index set of related items. It's finite, so it doesn't grow in size. It's a limited size here, and it only contains elements of the same data type. So if we declare a integer array, it's just going to contain integers, string array just strings, character array just characters, etc. Yes, and we can have multiple dimensions. We can have a single dimensional as well, which is in this example. So this array stores strings, so it's got the name George, Sue and Mo, and they're organized or accessed via their index. So our indexes in C# and many other programming languages start at 0. So 0 in this case would be George, 1 Sue, 2 Mo, etc. And we can have multi-dimensional arrays. So you can have a 2-dimensional array there, again storing some sort of string, possibly wall path, to make some form of maze, possibly. And this time you've got 2 indexes that you have to use to access the various different parts. So this middle path area here, I'll just get. So this one will be located at position 1, 1, and then depending on whether you've got the columns or the rows done first or second, it depends on which way round you might have this. So this path here could be at position 0, 1. Or equally, if you'd just flipped those around, it could be at 1, 0. Depends on how you've programmed that. So, moving on to something a bit new. What is an abstract data type / structure? Well, to start off, abstract data structures don't exist. Okay, they don't exist in their own right. So they make use of other data structures, such as arrays, which is why we just looked a moment ago and reminded ourselves of what arrays are. And they use this other data structure to come up with a new way of storing data. So if you're wondering what the term abstract means, existing in thought or as an idea, but not physical or concrete existence. So this isn't going to be something that really exists, it's just going to be something that we kind of force it to exist, possibly. Here's another one. In computer science, an abstract data type, a mathematical model for a data type where data type is defined by its behavior from the point of view of the user of the data. Now, these definitions aren't great, but they will make more sense in a moment when we do cover more about what a stack is. So, what does all this mean? Well, this video is going to help you construct your own stack, and a stack is a type of abstract data type. Inside the computer, we want to have stacks of data, but in reality, they're not going to have an actual stack in our computer. We're not actually stacking data up. We're just using memory, but we're going to have it behave like a stack. So we can pile things up, and then when we take off from the stack, we take off from the top. So piling the things on, pushing on, pushing on, pushing on, pushing on, and popping them off. Only taking from the top of the stack, only taking the last thing we put on. Now we're not actually, as I mentioned before, actually having this data stacked up, it's just in memory. Our abstract data type here, our stack, is going to behave like a stack. But in reality it's going to use, the one we're going to build anyway, is going to use an array. So the array is the real way we're storing the data, but our abstract data type, our stack, is going to help it to behave, or it's going to help from the point of the user, from the point of the user, point of view of the user, it's going to behave like a stack would. So as we place data on our stack, we can only add and remove from the top of it. Okay, so let's get into the basics of this. It's known as a LIFO data structure. That means that the last thing in is the first thing out. The last thing in is the first thing out. So where might we see real examples of stacks? Well, we could have a stack of chairs. Stack of chairs going on. So in this case, the last item that's been put on the stack is this blue chair. And the next item to get out of the stack, well, we'll be taking the blue chair off. The blue chair is the last thing on, the blue chair is the last thing off. We're not going to be getting the yellow chair out, not without first removing the blue chair and removing the green chair. Into the world of sweets, you may or may not have seen Pez dispensers, little sweets that you push into the dispenser, and then you kind of pull the head back and a sweet pops out. So yeah, the Pez dispenser there, the last sweet that you're going to put in is the first one that's going to come out when you push on the head. Another example for those people that enjoy first-person shooters, a gun magazine. A gun magazine, the ammo, you don't normally get to see inside. You don't normally get to see this bit, it's normally covered up. But when you're loading a gun magazine, you push the ammunition down, and when you are shooting, it's the ammo that's at the top that shoots off first. And there are many other examples of stacks in real life, but these are just a few that you might be aware of. So the commands for our stack, I've kind of mentioned some of these words already. Push. Push is the command that's going to put our data or our objects onto the stack. So this is where the gun magazine kind of is the easiest one to use to explain. because you actually have to physically push down the ammunition because there's a spring trying to push it out again. So you push down the ammunition until while you want to keep adding data. Pop, well, that's removing from a stack. So pop is going to be removing from a stack, popping off a stack. And peek allows you to see the top of the stack. Again, this chairs example isn't the greatest because you can actually see everything in here. You can see every element, every one of these chairs and what colour they are. When you've got the Pez dispenser and you've pushed in your sweets, you can only lift up the head a little bit and see the top one. When you look down on the gun magazine, you can see the top one. Yes, you might in some magazines you may be able to see the top two, but peeking just allows us to see what is at the top of the stack. And finally, we can have a few errors with stacks. Stacks are eventually, well, we can't have an infinite amount of memory, so we could potentially have too much to remember. If we've got too much to remember when it's on a stack, or if we've got too many chairs on our stack, or too many sweets going into our Pez dispenser, or too much ammunition going into our magazine, we're going to get something called stack overflow. So when we're trying to add to a stack that's already full, imagine we're trying to push our ammunition into our magazine when it's already full. It's not going to let us. In our computer, it's going to be a case of it'll run out of memory. So we need to be very careful of making sure that we don't try and add to an already full stack. And you might have heard these two words together before because they're on a very famous website which helps people out with problems, stackoverflow.com. And it's in regards to this type of error. Stack overflow, very common type of error. When you've got stack overflow, you've also got stack underflow, and that's when you're trying to pop off from a stack that's already empty. So in the case of the chairs, we've taken all the chairs off, and then someone's told you, go over there and get another chair. Well, there isn't one. Now you have common sense and you just won't crash. But a computer, when you tell it to do something that it can't do, is not going to be very happy with you. Trying to remove something from an empty stack would cause an underflow. Okay, so why do we bother learning about stacks? Well, it's because they're heavily used in computer systems. They form the fundamentals of a lot of things we do. On more simple levels, well, all of your undo and redo operations are covered by stacks. When you perform an action, say on Word, you perform an action, that action gets pushed onto a stack, an undo stack. And then you perform another action, that gets pushed onto it as well. And another action. Maybe I should draw this out. So some form of stack, and we type Dan. So we type Dan, then we pressed enter. So we went onto a new line. Then we type Dan again. Now, when we want to come and undo, we want to do the reverse of that action. And then we want to be able to press undo again. So and then we want to return to the line above, and then if we wanted to undo again, we're doing it in the same order that it was done in. It's about the order. Stack's going to help us do the order. And the redo, well, anything popped off of an undo stack can be pushed onto a redo stack. So that's some place you'll have seen it, but you've not realised that it's actually done on a stack. And the same with web browsers. When you're pressing back and forward on your web browser, you're going back to the previous website. So as you go through your different websites, they're going to be put onto a stack, and then you can go back, and you can go forward, and that's using a stack to help you with that. Evaluating mathematical operations. So this links to another part of the spec that we've got to cover. Computers don't like the ambiguity of brackets, so we can use a stack and reverse Polish notation to eliminate the need for brackets. So we can do any mathematical equation you want. We can evaluate it using a stack and reverse Polish. Give you a quick brief because we are going to cover it at another point. We currently like to do maths in infix notation. Infix notation is where the operator is in the between the two operands. So in this case, the 4 added to 2. Take 4, add it to 2. There would be nothing stopping us from writing plus 2, 4, which would mean add the next two things. The only reason we don't do that is because we didn't grow up with it. That's known as Polish notation. And then the same example in reverse Polish, 4, 2 plus. We've got the plus operator here, which is going to tell us to add the previous two things. So what would happen here is it'd come across the 4, put that onto the stack, come across the 2, put that onto the stack, come across the operator, which is add the last two things, and then our stack would look like that. Now, you don't really see the benefit in that example because we don't have anything with brackets. Say we had 4 plus 2 again, times by 3. Now, if we just simply took out the brackets and didn't have the brackets here and here, so it'd be 4 plus 2 times 3, you'd do the times 3 first. But that would get you a different answer from the 4 plus 2 and then times it by 3. So how would that be represented in reverse Polish? Well, 4, 2, 3 times. And we can write that without the need for brackets. So when it's evaluating it, I'm going to just go up here. When it's evaluating it, it pushes the 4 on, pushes the 2 on, it comes across the plus operator, which means pop the last two things and add them, and then it pushes the result on, so it's 6. We then push on the 3, come across another operator, in this case the times, and it will times the last two things, so 3 times 6, and push on the result. Eliminating the need for the brackets, eliminating the need for any ambiguity. That's a spec link that we'll come on to another time. The TCP IP protocol stack, it's even got the word stack in it. It's how the whole internet works, hence IP being in there, internet protocol. Again, as a spec link, we will go and cover that on the networking aspects of this subject. But yeah, a huge deal. The whole internet works in the same way. Everybody following the TCP IP protocol stack. The call stack, how your programs know what part of the codes to return to and what local variables were there. Again, spec link, it links to other parts of the spec. You need to know what the call stack is, and how it makes sure that we can return from when we've called from one subroutine to another. How does it know when to go back to, or what line to go back to? Well, it uses a stack to help us do that. And interrupt handling. So when we've got the fetch execute cycle going on and on and on and on, and somebody interrupts us, or something interrupts us, the registers are pushed onto a stack, the interrupt's handled, and then they're popped back off the stack. So they're a pretty big deal in computer science. Don't worry too much about the reverse Polish. That was a quick brief for you. If you're interested, yeah, go ahead and research it and find out. It's always fun when you do a math homework and give it back in reverse Polish and see what your math teacher thinks about that. Right, a quick past paper question for you then. So you're given a scenario, so there's some memory locations, so this part over here is just indicating memory, and we've got addressable memory locations here. It's just given us 6 of them, 600 to 605, and they're to be used as a stack to store the character and data. The first value is to be added to address 600. Okay, so this is going to be our starting point in our stack, 600. Okay, so the question: show the state of the stack after the characters A, V, E, R, and Y join the stack. So in this case, A is the first thing that's going to be put on there. So this is where our stack is beginning. So A would be there. And then we're kind of pointing to the next space in our stack. So in order to add to the next one. So we add the A is added there. And then we're going to move kind of where our stack is starting, or the top of our stack, which seems a bit odd given that we're going down. The top of our stack, V. So the top of our stack now there. The next character, E, well, the top of the stack is going to be there now. And we add E into memory. Next one, R. Again, this arrow, I'm going to call it a pointer. I'm going to point to the next location and then enter that data. Push that data on. Let's use the command words. Push that data onto our stack. And finally, Y. We've got that pointer moving up, pointing to the next location and entering our data. So the top of our stack is at 604. So they've all been stored in these memory locations, and the top of the stack is there. So for those that like visuals of the top of the stack actually being at the top, the Y is there, the R, the E, the V, and the A. Just actually in memory location 600 to 604, that's the other way around. So, question then goes on and suggests that 2 items are removed from the stack. So this would be a case of popping twice. So if we look at our visualization here at the top, popping removes from the stack. So if we're removing from the stack, we're going to take a copy of the Y, and then the pointer, because Y is not going to be essentially there anymore, pointer would move down. R would now be the top of the stack. If you imagine back to those chairs that we looked at, took off the top chair, now the top chair is the one below the one we just took off. The same again here, we're asked to remove 2 items, 2 items. So the R is also going to be removed. So the top of the stack is going to end up being the E. So our stack's just going to be EVA. Now officially, R and Y will still be in memory. They will still exist in memory because we've not overwritten those memory locations. And we've not deleted them. We just can't, in the terms of a stack and how a stack works, we just can't access them anymore. So our top of stack is going to be E. So let's write it in here, so in this way. So we've got A, V, E, and here's my top of stack. So I'm gonna also put in there just so you're aware. The Y and the R are still there because we've not overridden them, but the top of stack is actually E. And they've not been deleted, or overridden. But the top of stack is only going to point to the E. Question then goes on to add 2 new characters, S and P. So back to this visualization here. So we've got the A, V, and the E. We know they're in our stack, and our top of stack is E. Now, if we're adding to this stack, we'll need to move the pointer up to the next available space, and then put in the next character, which we're told is S. So the S gets put in, or pushed in. And then to push another one, top of the stack pointer needs to move up 1, and we put in P. So our final stack, A, V, E, S, P, with the pointer to the top of our stack at P. So if we were to remove again, P would be removed and then the pointer would move to S. If we were to add again, we'd move the pointer to the next space and then add the data item. So our stack really just consists of some sort of structure for our data. So in this case, they've got some memory locations, but this could easily be an array. And then a pointer to indicate what element we're looking at. Remember, this stack it's an abstract data type, so it doesn't really exist. It uses another data structure in order to store the data, and what it does, the behavior of it makes it behave like a stack, like we've just piled things up. In this case, we've got A and then V on top of that, and then E on top of that, and then S on top of that, and then P on top of that. And the only way we can get to V, let's say, would be to pop off P, S, and E. Okay, so now we're going to build our own stack. So we've come up with a little design, an object-oriented design. Here we've got a class diagram. We've got the name of the class, so I'm just going to call it my stack. And then we've got minus here, which is indicating a private. It's about the access modifiers, indicating that it's a private data type. In this case, I've called it top of stack PTR, PTR standing for pointer, and I've decided that it's going to be an integer. My pointer is going to be an integer. Again, next up, we've got a private attribute, stack contents, and this is of type char, and it's an array of characters. So the stack we're making here is going to be able to hold the information that we had when we just did our past paper question here. It's going to have characters within it. And then, so they're the only attributes we need for our stack. we need a pointer to indicate what position we're looking at in the stack, or what the top of the stack is, and then we've got some operations, some methods, and these methods, see, most of them are pluses, and that's standing for the public access modifier, so these can be accessed from outside this class. The minus ones, the private ones, can't be accessed from outside. And so I've got all of these. Push. Now push is going to accept a letter. It's not going to do anything with it. It's going to be void. Push is just going to add to our stack. So we're going to have an attribute that we send in. So we're going to send in an argument, a letter, and it's going to push that onto the stack. Pop. It's going to be a function. Okay, so it's not void. Void indicated to us that it doesn't return anything. It's a procedure. Char here indicates that it's going to return a character. So pop's going to return a character to us. Next up, peek. Peek is just going to allow us to look at the top character. So if we were to have a look at this example, if on this point here, if we were to do a peek, it would return P. And the pointer would remain in the same position. Because peeking is just having a look, not popping off the stack. So it just returns whatever's at the top. Going back to our real life examples, peeking, we'll be able to take a look at what the first suite is. Peeking, we'll be able to take a look at if there was some top ammunition there. Peeking, we can see what is at the top of the stack only. Okay, if we were to peek on this one, it should return E, and the pointer would remain in the same position. If we were to peek here, it should return Y, and the pointer will remain in the same position. And then I've got these two extra methods, isEmpty and isFull, both of which are functions returning a Boolean value. Got isEmpty and isFull, and the reasons behind having those as well is that we need to be able to test for an empty stack and a full stack so that we can try and avoid stack overflow, trying to add to a stack when it's full, and stack underflow, trying to add to a stack when it's empty. So I'm going to move on and make our stack now. I'm going to make a console application for this. I've called it Stack Demo. And we're going to build our stack class based on our design that we just had there. As we go through, I'm going to ask you to pause as you go through and kind of have a go at making it yourself. Have a go at making parts of it yourself, and then playing the video and seeing maybe an alternate way or a solution because you got stuck. Right, so you get the bog standard default start here, just an empty main and a class program. I want to right click on our stack demo and add a new class. So a new item, class, and we're going to call it, because we're going to follow the design I showed you a moment ago, my stack, so as not to interfere with any built-in C# stacks that exist. Okay, and my stack, we said we'd have two properties. So my properties for this are going to be an integer, top of stack pointer, PTR. And what I'm going to do initially is set that to be -1. Because when we've got an empty stack, we don't want it to point to the top of it. Well, there is no top of it. So we're going to have it as -1. And that's a typical thing you're seeing in a variety of different languages. For example, when you do a search for a letter within a string, there's built-in commands for that, and what they'll return to you is the position in the string that the letter is, or -1 to indicate that it's not in there. So we're going to follow that same sort of style. And the top of the stack, well, there is no top of the stack. It's -1. There isn't anything in our stack. And for us, we're making a character array. Stack contents. And then we need some methods. So for our methods, we had public push. So we have push, and that would accept a letter and attempt to push it onto our stack. And it was a procedure, so void, public void push. I'm going to just make the outline, the skeleton for this, and do the rest later on, and do the coding in a bit. Public pop. It didn't require public char because we were returning a character. Pop. It didn't require any information coming in, and just to stop it having a red line, just going to return null for now. Returning nothing. Can I not do that? Return a blank character then. There we go, blank character. Public char peak. Again, not requiring any parameters because it's just going to return to us whatever is at the top of our stack. And then we've got private booleans for is empty. Return false, just to get rid of red lines, nothing else. And private bool is full. Okay, so we've got our skeleton stack. We've got our properties, which we did say that they were going to be private. Now you notice I didn't write private in front. I can do. But if you don't write an access modifier in front of them, by default they will be private. But we've explicitly said it there. So we've got a private top of stack pointer, which we're pointing to -1 because -1 can't exist in our array positions. So that's telling us that it's currently empty. There's nothing in it. And then we've got our array, which is going to be our stack. We're just going to also include a constructor. So the constructor is going to help us to create an instance of the myStack class. A constructor always has to be the same name as the class itself, and we're going to put in a integer called size, because I want to, when I construct my stack, it to know what size this array's got to be. So when I create my stack, I'm going to pass in a size, and the array is going to adjust to that size. So stack contents equals new char array of size. When we make a new instance of the array, we make the array the size that we're after. So if I created a new array of size 20, come in here, if I made a new my stack and I passed in 20, we make a new array of size 20. Okay, so first up, we want to deal with the errors first of all. Is empty, is full. The easiest one to do will be is empty. Using the properties that we've got here, top of stack and or stack contents, we should be able to tell whether the whether the stack is empty or not. So pause the video here, have a go at creating or writing your is empty subroutine. Okay, hopefully you've had a go at that. Is empty. Well, this is the only information that we've got about our stack. We've got the top of stack pointer and we've got the stack contents themselves. In order to find out whether something's empty or not, it's really revolving around the top of the stack pointer. If the top of the stack pointer is at -1, that's indicating to us that our stack has got no items in it. So the only thing we need in this is empty. We can do some if statements and all sorts of fancy things in this, or we could do top of stack pointer equals -1. Because we've used that is the equals, that's going to give us a Boolean answer. It's a comparison. So is top of stack pointer equal to -1? If it is, that would return true. If it isn't, that would return false. If the top of stack pointer is -1, it is empty. Okay, next up is full. Pause the video, have a go at working out whether you know whether it's full or not. Okay, so hopefully you've had a go at that. Doing a similar thing here, we can use the top of the stack pointer. Top of stack pointer, if it is equal to the size of our array, so stack contents dot length, but not just that. Say if we had our stack contents length was 20, that means that this top of stack pointer would have to equal 20 in order to be full. But we must not forget that the array positions start from 0. So if the stack content was 20 in length, the highest position in it, the highest index, would be 19. So it's whatever the length is -1. If the top of stack pointer is at that position, then it is full. And instead of using if statements and things, we've just got the comparison done here in the return. So if the top of stack pointer compared with the stack contents length -1, then it is full. So we've sorted out those two things. Those two things are going to help us to avoid errors. Next up, push. We want to be able to put onto our stack. Okay, and we want to be able to do it error-free. So you must make sure that what you're doing is right. So pause the video here and have a go at creating the push function. Okay, so hopefully you've given it a go. The first thing we need to do before we go and put a letter onto our array is we have to check whether the array is already full. So we can call the method that we created a moment ago. So is it full? If it is, we'll just output an error. And we'll use the name of the error correctly. Stack overflow error. Quite angry in caps lock there. Stack is full. Could not push. So we've got an error there. You could write whatever error you want. However, if it is not full, so if that comes back false, we want it to do something. We want the top of stack pointer to increment, because if it's empty, it starts at -1. We want the top of the stack pointer to be at position 0 in our array. If it's at position 0, we want it to be in position 1, ready to add to the next thing. So we increment the top of the stack pointer, and then the stack contents at top of stack pointer equal, well, it's going to be the letter that we send in. The letter that we send in itself. So that moves up the pointer, like we showed in our examples earlier on. Having the pointer move, then add the letter. And that's the push. Before we go any further, we should actually test this out, see if it works. So if you go back to your program, the main, and we can start finding our stack. My stack equals new my stack, and you see that it comes up with int size. So let's give it a size of 3 to begin with, and then have a look at what we can do. Now we can see all of those public methods that we had, peek, pop and push, all public, and we can see them all here. Now we know that we've only coded push, so there's no point trying to test the others. So we can push things. So push d my stack dot push a my stack dot push n. That should work fine. It should push those 3 items on because the size of my stack was 3, and my stack dot push, if I do it for a 4th time, I should get an error. When we run it. Console.readline just to stop the program so we can see what's going on. And if we give that a run, what should happen is we get a stack overflow error, but just the one, hopefully. yeah, we get the one error. Stack overflow error, stack is full, could not push. Just to prove it, if we just copy that last one again and push it on. So now we're trying to, we push on D, we push on A, we push on N, and then we're trying to push on N 2 more times. So we should get 2 error messages this time. Yeah, 2 overflow error messages. Excellent. And if we go into the code here, if we put a breakpoint in, we can prove that we're actually adding the letters into the array. The breakpoint will stop it at that point in the code, allow us to step through. So we step through the code, the N has been passed through to here. Is it full? No, it's not. Oh, you need to check first. That returns back false, it's not full. And we see that the top of stack pointer, which is currently at 1, increments to 2, and then we're putting our stack contents in at 2. So we've already got D and A in. When this line executes, N would be in. D, A, N, fantastic. So it is adding data to our stack. And it is dealing with the error of pushing. Okay, next up, pop. Again, pause the video, have a go at creating your pop. Okay, so based off last time, we need to first check for errors. This time we're not bothering to check if it's full when we're popping, because we're trying to take things off. So we need to check for if it is empty. So we've got something to help us do that. So we made is empty. So if we try and call that is empty, we're first checking if it's empty or not. If it is empty, well, we don't really want, we want it to tell that there's an error, so we want it to be an error message again. Oops. We want it to be an error message again. So error stack underflow. The stack is empty. Stack is empty. Okay, so that should come up with an error if that's true, and just going to get it to return just a blank character. However, if it's not empty, then we want to be able to remove it from the stack. So previously we incremented the stack pointer and then we changed or added the letter to that position in the array. There's a number of ways that we could do this. We could have the top of the stack pointer decrement and then return the letter that we were looking at. In fact, we're gonna do it in a better way. We're gonna create a temporary character, temp, and set that equal to the stack contents at position top of stack pointer. Then the top of stack pointer can decrement because we don't want it to be pointing to that one anymore when we pop it off. and return our temp, our temporary value. So it goes to the position being pointed to, copies the character, reduces the position of the one you're pointing to, and returns it. So if we just go and test this out then, so mystack.pop, and we want to do something with that. So if we do console write line mystack.pop, and just so we're able to see which one we're talking about, I'm just going to say pop1 and then call mystack.pop. So pop1 in our stack here of 3, push on D, push on A, push on N. It has an error with that one and an error with that one. And then if we do mystack.pop, it should return to us this N character, and it'll output pop1 N. Do a similar thing. Pop2, it should pop off A. And pop, and then change it to 3 so we can see it clearly. It should return D. And then if we call, if we do the same thing again, well, it should be empty by that point, so it should give us an error, and this will return a blank space for us. So pushing on D, pushing on A, pushing on N. It's too full for that one, it's too full for that one. Popping off, we pop off the N. Popping off, we pop off the A. Popping off, we pop off the D. Popping off, well, there's nothing to pop off, it's empty. It should output an error message to us. So let's see that in action. So we've got the 2 Stack Overflow errors as we had before with our pushing. We pop off the N, pop off the A, pop off the D. And it's in the correct order. It's in the LIFO order. The last one in is the first one out. The N was the last one in, the N is the first one out. The A was the last one in, or the second to last one in, pops that out. The D was the first one in, but there's nothing else left, so it has to pop that one out. And we get the underflow error when we try and pop too many times. Excellent. So we're very close to being completed here. Last up, by no means least, but far easier than the push and the pop, is the peak. Again, pause the video, give it a go. Okay, so the peak, really quite easy, very similar to the pop, except you're not having to deal with the top of stack pointer decrementing. So we could reduce the code for the pop in the future and have it call peak, but for now, we're just going to make peak on its own. We still do need to check if the if it is empty before we bother peaking. So we've still got the is empty and a stack underflow, and yeah, we just don't need the pointer incrementing or decrementing. So we just need to have it return the top of stack pointer, because it's not actually changing our stack. It's not removing or adding, it's just looking at the top thing. So it's just looking at whatever's at the top of the stack, peaking. Just like that. Okay, so if we introduce it to this, I'm going to change up my testing. So So I'm going to do peak 1 and have it peak. And then my second peak I'll do here, peak 2, and my third peak right at the end. So what am I anticipating happening? Well, we've got our stack, it's 3 in length. We push on 3 characters, D, A and N. We try and push on 2 more, it's going to give us 2 errors. Error, error. I then peak. I anticipate that this would return to me N, because N was the last thing that we pushed onto the stack. We then pop. Well, that's going to give me N as well, because that was at the top of the stack. We pop for a second time. That's going to return to me A. Then I peak for a second time. Now it should be D. Why not A? Well, we popped it on the last line. So D is the top of our stack now. Try and pop again. Well, that should return to me D. And try and pop again. Error. And finally, try and peak. Well, we've popped everything off, so it should be an error. So I'm expecting 2 error messages, a peak with an N, a pop with an N, a pop with an A peak with a D, a pop with a D, a pop with an error, and a peak with an error. See if we get what we're expecting. So here we have the 2 errors. We could not push. Then we have our peak. We had a little look, N. Peak didn't remove it, so when we come to pop it, it's still N. The top of our stack is still N. When we pop for a second time, we pop off A. Let's make this a little bit bigger. We pop off A. And now D is going to be the top of our stack. So when we peak, we get D. When we pop, we get D because the peak does not remove. It just looks at the top item. When we try and pop again for the 4th time, well, there is only 3 items in there, so the stack is empty. That's an underflow. And the same goes for when I try and peak. Well, it's empty. There's nothing to peak at. So that video gives you the basics of stacks and how to create them, what they're all about, why we bother to do it. So we covered what a data structure was, we covered what an array is, or reminded ourselves what an array is. We now know what a abstract data type is. Data type doesn't really exist. It's one that's got to use existing data types, and it's just about the behaviors that are changing. The stack basics, why learn about stacks, the question of it, and building our own stack. And what you can go and do now is have a test and play around with the stack that you've created, possibly go and have a go at that past paper question and see if you get the same results, pushing those letters on, popping off. And that's it.